In the previous class, we discussed the propagators in quantum field theory and their important properties. So you can get them without any detailed calculations, just based on symmetries. But in this class, let's compute those functions explicitly. So let's start with g plus of x prime. So we have seen that it is the correlation of phi of x and phi of x prime in the vacuum state. So if I write all of them explicitly, then I will get integral d cube k by 2 pi cube. Then for phi of x prime, I have to write d cube k prime by 2 pi cube 1 by root of 2 omega k, then 1 by root of 2 omega k prime. Then I have the correlation. Okay, first for phi of x I can write ak uk of x plus ak dagger uk star of x. Then for phi x prime I can write ak prime uk prime of x prime plus ak prime dagger uk prime star of x prime. Okay, so this kind of integral we have seen in the last class. So here you have to again expand. So ak prime, then ak dagger, ak prime dagger, then ak dagger ak prime, and ak dagger ak prime dagger. And when you take the integral, almost all of the terms will cancel, and what is left? Integral d cube k by 2 pi cube, and there will be a Dirac delta because you can write it in terms of the commutator of ak and ak prime dagger, right? So the expectation value will be a delta function, and one of the k or k prime I can use to integrate the Dirac delta because it will be of the form k plus k prime. So once I integrate, then I will get only one term, that will be, and here 1 by root of 2 omega and 1 by root of 2 omega k prime will become 1 by 2 omega k, and the only function that is left will be e raised to minus I omega k t minus t prime plus I k x minus x prime. So this will be g plus of x prime. Okay, so let this be equation number 1. We'll come back to this. Now I can also rewrite this equation for g plus in another form. I don't know how many of you are familiar with this form. I can write g plus of x prime as integral of d raised to 4k. So you have to note here it was d cube, and here it is 4 because I am integrating the time also into this integral by, so I have to write 2 pi to the power 4, and I am multiplying a 2 pi here. Okay, then I am writing theta of k naught delta k square plus m square. Then this e raised to I k x minus x prime I will write as it is. K x minus x prime as it is. So this part I can write as theta of k delta of k square plus m square. Okay, so I'll just explain why this form appears. Okay, this is not compulsory to write it in this form, but you can also write, this is another form. Okay, another form of G plus. Okay, so how it comes? So imagine the energy momentum space that any relativistic particle can take. So if you have a relativistic particle, the energy will be E square is equal to P square plus M square, right? In K space, I can write this will be K square plus M square because P is equal to H cross K. Fine. Then the energy can take plus or minus root of K square plus M square. Then if I take the energy and momentum space, if I consider energy here and the K here, then E is equal to, there are two solutions, plus root of K square plus M square and minus root of K square plus M square. So this will be positive energy solution. It's a hyperbola, right? I have here also. And the distance of this hyperbola from the bottom axis, okay, this distance will depend upon the mass. Here it will be plus m and here it will be minus m. So distance of the hyperbola from the k axis will depend on the mass, and the radius of curvature will also depend on the mass. For example, you are considering a massless particle. If it's a massless particle, then m will be equal to 0. Then the curve will be not like this. It will be something like this. Okay. And similarly here it will be something like this. This is if m is equal to 0, because this distance will depend upon mass, and also the radius of curvature of the hyperbola will also depend on the mass. And if you have more mass and less mass, if you have some mass m, then you will have this curve, these two curves. Okay, if you have more mass, then it will be here, right? And here it will be here. This is for more mass, if you have more mass. So the distance of the hyperbola from the axis is determined by the mass, and also the radius of curvature is determined by the mass. So this is for one-dimensional case. If it is in 3 dimension, then this is called a mass shell, because it's no longer a hyperbola, but you will have something like this in 3 dimension. So it is called as mass shell. Okay, and you have both positive and negative energy mass shell. While integrating in K space, I just want to pick out only those momenta that are on shell. Okay, which means that here I can have any number of energies and momentum, but I only want those momenta, I have to pick out those momenta that are on the shell or on shell. It's called on shell. So we use the term on shell. Okay, this is mainly for scattering between particles and the scattering theory. Okay, but now just we'll define that I just want to pick out those momenta that are on shell that corresponds to real particles. So why do I say on shell? Because on shell momenta means the momenta corresponding to the real particles. If there can also be virtual particles that we'll see later, but for those virtual particles, their momenta will be off shell. Okay, so here on shell means the momenta corresponding to the real particles. So I have to pick out those momenta that are on shell. So the general equation for a particle in the Klein-Gordon equation without any interaction. So we are seeing without any interaction till now. Okay, it's called as free scalar field theory. Free in the sense there are no interactions. So for such a particle, you can write the wave function as, so this is the general form of the wave function for a particle in the Klein-Gordon equation, free scalar field theory. It is given by integral d4 k by 2 pi 4. There will be e raised to minus I k dot x. Okay, and there will be a complex coefficient for the momentum. So let's define by C. This is the complex coefficient for momentum, and there will be a Dirac delta which will be of this form. Okay, so this Dirac delta selects out the 4 momenta that are on shell. Okay, that is a function of this Dirac delta. It selects out just the 4 momenta that are on shell. Okay, so that is how you get this form. So here this theta of k naught represents the complex coefficient of the 4 momentum, and this Dirac delta is used to select out the momenta that are on shell. Okay, so therefore I can write G plus in another form also. Okay, so in this new form, K is unconstrained. If you see the new form of G plus, this K is not constrained. Okay, but the Dirac delta function enforces it on shell. So there are no constraints. Here integral of d4k means I am integrating over all the k values. But how do I select the on shell momenta? So that function is actually carried out by the Dirac delta function. Selection of on shell momenta is carried out by the Dirac delta function. Okay, so there are no constraints for k in the integration, but the constraint is actually enforced, okay, enforced into this function by the Dirac delta. Okay, so similarly you can also find the integral expressions for gr, ga and gf, the retarded, advanced and Feynman function. Now g plus x prime is actually the overlap of x and x prime. This also we have seen in the last class. Now let's calculate g plus 4 equal time. So for equal time, t will be equal to t prime. That is meant by equal time. For equal time, if I want to calculate the explicit expression for g plus for equal time, then I have to substitute t equal to t prime in the equation number 1. Right? So here I have to substitute t is equal to t prime. then I will get g plus x prime is equal to integral d cube k by 2 pi cube 1 by 2 omega k e raised to, when t is equal to t prime, t minus t prime will be 0. Then I have e raised to I k x minus x prime. So you can see that clearly this is not equal to 0, right? This is not equal to 0. So that's why we said earlier that this is not a localized state, because g of x prime means it is the overlap of x and x prime. So clearly we can see that even at equal time, this correlation is not equal to 0. Therefore, this state is not localized. Okay. So at t is equal to t prime, the Green's function g plus, or the Wittmann function, is not proportional to delta function. Okay, and because of the presence of this omega k, so I will not get the Dirac delta function, and therefore clearly we can see that this is not equal to 0 and the state is not localized state. Also, if you see this equation, it is based on rotational symmetry. So it depends only on the separation between x and x prime. Suppose if I write the separation between them as r equal to x minus x prime. Let this be the separation between x and x prime. Then the integral will be g plus of r. The integral will be proportional to the modified Bessel function. See here, I cannot directly integrate this function. It's a complex function. So how do I integrate this? To integrate this, I need the Bessel function, and the solution will be, so we don't have to do the direct integration. I'll just write proportional to the Bessel function mr. Okay, so this will be proportional to, approximately equal to e power minus mr. Okay, now at large distances, okay, large distances in the sense mr must be very much greater than 1. At large distances, r is very much greater than 1 by m. Then e to the power, if r is very much greater, then I can write e to the power, mr will go to infinity, it will tend to infinity. So e to the power minus infinity, then g plus will be very small. So g plus will be very small. But we have seen that g plus is not equal to 0, right? G plus can be very small, but g plus cannot be 0 because it's not a localized state. Then what does this mean? So in some sense, g plus is approximately a localized state. It's not a localized state because it cannot be equal to 0. But in some sense, if you think, then g plus can be approximately a localized state. Approximately a localized state. That is, for r very much greater than 1 by m, g plus is exponentially small. So this is not a perfectly localized state. It is localized up to a distance 1 by m. That is, if you have x here, okay, then if you have x prime here, so this is the distance r, then the state is not perfectly localized state, but it is localized only up to some distance 1 by m. So if these 2 points are separated by more than 1 by m, then the overlap becomes very small. So we call this 1 by m as psi. Okay, psi. So this is known as the correlation length. Psi is called as the correlation length. So up to this length, you can find some correlation between these 2 points, and beyond this length, you cannot find any correlation between these 2 points. So when the distance is beyond psi, the field is no longer correlated. So in this sense, this is approximately localized object, and it is the Compton wavelength of the particle. So once you go outside the Compton wavelength of the particle, then the overlap becomes very small. So rather than the coordinate space expression often used in quantum field theory, the expressions are all in momentum space. Therefore, we have to consider the Fourier transform of all the functions. So far we have seen g of x prime, and g plus g minus gr, ga, gf, everything in terms of x prime. But we have to consider the Fourier transform of all the functions. So the Fourier transform of g of x will be g of k. So here whenever I write just g, it means it represents ga, gr, gf, g plus, g minus, etc. Okay, so these are all Green's function. So if I just write g, means it's a general expression. So g of k is equal to integral d4x, then g of x e raised to minus I k x. So this is the Fourier transform of g of x and its inverse Fourier transform. So whenever I write the inverse Fourier transform, I need to write x and x prime is equal to 2 pi to the power 4, then g of k e raised to I k x minus x prime. So this is the inverse Fourier transform. This is the Fourier transform. This is inverse Fourier transform. Now if you compare this with equation 1, the equation that is just after the equation 1, that is another form of g plus, yes, this equation. So if I compare this g plus, then I have to find the analog of theta and delta of k square plus m square. So if I compare these two equations, then I can write g plus of k is equal to 2 pi theta of k0 k square plus m square. Okay, so this g of k or g plus of k will be 2 pi theta Dirac delta of k square plus m square. So this is the expression for g plus in the k space. Now without repeating the above procedure, so without writing the Fourier transform and all these explicit forms and then comparing and finding out, for gr, ga and gf, we can get the momentum space expression very easily from the property 1 that we discussed in the previous class. So previous class we discussed 3 properties, remember? So in the first property we said it's much easier to start deriving gr, ga and gf in k space from the first property. What was the first property? Minus del square plus m square g r a f is equal to minus I Dirac delta in 4 dimension x minus x prime. So taking the Fourier transform on both sides, okay, we get, so Fourier transform of del square will be minus k square. So minus del square will be k square plus m square, then the Fourier transform of GRAF of x will be GRAF in K space. This will be equal to minus I, because the Fourier transform of Dirac delta is 1. So this is very simple. So rearranging, I get GRAF of K is equal to minus I by K square plus M square. But we have some problems here. So the first problem is that when K square is equal to minus M square, then G of K will have a singularity. This is the first problem. Then second problem is that this expression says that GR is equal to GA is equal to GF is equal to minus I by K square plus M square. There is only a unique solution for all these functions. But that should not be the case. It's not always the equal. So I cannot get a unique solution for all the functions. Okay, but if we calculate them going through all the steps that we mentioned just before, then you will get GR not equal to GA. So when I went for the easy method, okay, just taking the first property and then taking the Fourier transform, then I am getting a unique solution. So if I have followed the earlier procedure, then I may not get this problem. But that is more complicated, right? Taking all the steps, doing all the steps is much more complicated. So I need to follow the shortcut method, but I have to get different values for GR, GA and GF. So looks like these two problems are related. Okay, so I have two problems. One is singularity and another one is that for all the functions I am getting the same value. So these two problems look like they are related. So if I solve one problem, the other will get automatically solved. So I can write the inverse Fourier transform for G of K. If I write, then I'll get G R A F x minus x prime is equal to, how do I do the inverse Fourier transform? D for K by 2 pi to the power 4, then the function minus I by K square plus M square e raised to I K dot x minus x prime. So here 1 by K square plus M square is equal to 1 by, so this K square is not just K square, it has K0, K1, K2, K3, all these squared. So this will be time, this will correspond to space. So the time part I can write minus omega square, and the remaining spatial squares I can write K square, then plus M square. Okay, I am just expanding the K square here. Okay, it is a 4 momentum. So I am just expanding it in time and space. Then you will ask why there is a negative sign here, because I am following the Minkowski metric. Fine, minus plus plus plus. Now this is equal to K square plus M square. We have already defined it as omega K square. Therefore I can write 1 by minus omega square plus omega K square. So when omega is equal to plus or minus omega K, there is a singularity. There is a singularity. And where is this singularity present? This singularity is along the integration contour of omega. That is, if you see here, there is integral of d4k. So integral of d4k is the contour. So I can split this contour as integral d omega and dk. So here you have the three-dimensional space, and here you have the time component, and that is d4k. So I am splitting it something like this, and the integral will be minus infinity to plus infinity. So this is the integration contour of omega. So if you look at the omega axis, okay, if I have an axis containing omega, then the singularity is present at, this is origin, singularity is at plus or minus omega k, right? Singularity is present in plus or minus omega k. So if this is the origin, plus omega k and minus omega k. Okay. So the integral is not well defined. So in order to define this omega integral, we have to do a trick in the complex analysis. Okay, so along the contour is minus infinity to plus infinity, but the integral is not well defined because I have a singularity here and here. So I have minus infinity here, plus infinity here. The integral is not smooth. I have a singularity. I have two singularities at minus omega k and plus omega k. Therefore, the integral is not well defined. So in order to define this omega integral, we have to do a trick in the complex analysis. So I have to go around the singularity. Okay. Which means you have to consider a complex plane. If this is the complex plane, here you have the real omega, here you will have the imaginary omega, then this is the origin, here you have omega k, plus omega k, and here you have minus omega k. Okay, now the integration contour is along the real axis. So here we have seen the integration contour is along the real axis. And I have four choices. If I want to go around the singularity, okay, I have to bypass the singularity, then I have four choices. Either I can go like this here, and then go like this, and go straight, and again bypass, and go like this. This is so one choice. Another choice is I can go like this and go below, right? And then again go like this and go below and continue the integral. So I have four choices. So this is one choice, this is second choice, and the third choice, one singularity I can bypass from above and another singularity I can bypass from below. That is the third choice. Then I can do one thing. First one I can bypass through below, and the second one I can bypass through above. So there are four choices that I can, four ways to go around the singularity. Okay. So each choice will correspond to a solution, and therefore we have four solutions. So earlier we had only a unique solution, gr, ga, gf is equal to minus I by k square plus m square, and there was a singularity. So that was our problem. So once you try to remove the singularity, then I am getting four solutions. So both of these problems will be solved. So that's why I said these two problems are related. If you have a singularity, then gr equal to ga equal to gf. If I try to remove the singularity, then I get four different solutions. So you will ask me, there are only three functions here, gr, ga, gf, but you have four solutions. So what are you going to do with the fourth solution? So actually there is gf and gf tilde. Okay, but in quantum field theory, we don't use gf tilde much, and therefore we usually don't talk about it. Okay, so these four solution corresponds to GR, GA, GF and GF tilde. So there are four solutions. So let's do one by one. So if you remember, we have defined the retarded function GR as proportional to theta of t minus t prime. Okay, which means this function will be equal to 0 if t minus t prime is less than 0, which means t less than t prime. So if t is less than t prime, then GR will be 0. So how do we achieve that? By going around the poles? That is the question. Okay, so in our expression for GR, okay, so this is our GR. Here I have e to the power I k x minus x prime, and this x is x and k are 4 momenta and 4 space, because here you have d to the power 4k, d4k by 2 pi 4. So both space and time is encoded here. Okay, so if I take e to the power I k dot x minus x prime, okay, and if I try to separate it into the time component, then it will correspond to e raised to minus I omega t minus t prime. Why minus here? Because Minkowski space. Time part will be negative, space will be plus plus plus. So I am following the sign convention, minus plus plus plus. Okay, so time part will always be minus and space will be plus. So if I separate the time component from e raised to I k dot x minus x prime, I will get e power minus I omega t minus t prime. Fine. Now here t minus t prime, for our retarded function, it should be less than 0, which means t must be less than t prime. Therefore t minus t prime will be negative. So already there is a negative outside. This quantity will also be negative. So negative and negative, it will be positive. Okay, which means omega will be in a positive plane. It has to be in a positive plane. Fine. So for exponential decay to happen, omega has to be positive. Only then exponential decay will happen. That is, omega has to be integrated through a contour that is closed in the upper half plane. Okay, so the contour has to be closed in the upper half plane. So this is the plane for omega. Here you have real and here you have imaginary. Then the contour should be, if I start the contour from here, it should go like this, and then it should get closed in the upper half of the plane itself for GR. Now we are seeing the first solution for GR. So for GR, t must be less than t prime, which means t minus t prime will be negative. Already there is a negative outside. So for exponential decay to happen, omega has to be positive, which means that the contour must be closed in the upper half plane. Then the solution corresponding to GR will be, so here you have a singularity, here you have a singularity. Okay, so the contour starts from here, it comes here, something like this, and then it comes here, then it will go like this, and from here it will get closed like this. So here minus omega k plus omega k. So when you go above the singularity, there is no singularity in the contour. You can see the singularity is avoided, right? So you go like this, avoid the singularity, avoid the next singularity, and close the contour in the upper half of the plane itself. Similarly, for advanced function GA, so this is the second solution. So we have seen the first solution, this is the first solution. Second solution is for advanced. So we have seen that advanced Green's function is proportional to theta of t prime minus t. So here it was t minus t prime, but for advanced function it is t prime minus t, which means that t prime must be greater than t. Then you must go in the opposite direction. So if you have something like this, then you have to go in the opposite direction. You have a singularity here and a singularity here. You go in the opposite direction, okay, and close the contour in the opposite direction. Similarly, for Feynman function gf, so there is gf and gf tilde, right? So I'll discuss only about gf. So for the time being, we will not see gf tilde. So one has to go up and one will go down. So in the case of gf, it will be, if you have singularity here, then here you have to go below and go like this, and here it will be above. Okay, so this will be real omega, imaginary omega, one up and one down. So if you have to specify a contour like this each time, it is not convenient. So there is another way to tackle this problem, all in one method. So always keep on avoiding the singularity and changing the contour. It is very difficult. So here what method we have used? We have changed the contour. So instead of going along the axis, real omega axis, I am deviating from the axis and again coming back, again deviating and coming back, right? So I am actually changing the contour. So this is not convenient. Changing the contour always is not convenient, okay? And we have to, the best method is that we have to try to move the singularity. So instead of changing the contour, I can move the singularity. If I have a singularity here and if I have a singularity here, I can shift it a little bit downwards, and I can shift this singularity a little bit downwards, and without changing the contour I can just go straight. So that will be an easier method. Okay, so for this class we will stop here, and in the next class we will see the next way of integrating without changing the contour.